Thank you for the invitation to be at Daisy. I wish I could be there in person, enjoying the warmer weather in Florida as compared to Indiana. However, I am grateful for Zoom and virtual recordings. I hope this presentation on machine learning measurement bias will be helpful to the theme this year of tackling bias in data science. Before I begin, I want to acknowledge that this talk that I will be presenting is based on a paper with my co-authors, Sang Wu, Lewis Hickman, Brandon Booth, Sydney DeMello. This work is also funded from the National Science Foundation and the PSYOP Anti-Racism Grant as well. So I'm very grateful to my co-authors and my funders. There are several issues that I want to address in this talk. First of all, how do we define bias in machine learning models, particularly for human assessments? And by human assessments, I mean things like human attributes and traits such as personality, health status, health conditions, and so forth. What are the different sources of bias in machine learning models for human assessments? So not merely defining the bias itself, but really trying to understand the different sources of biases. By understanding these different sources of biases, we can then go on to try to mitigate these sources of biases. So I have some preliminary proposals on how we might go about mitigating some of these sources of biases. And finally, what are some of the practical recommendations for users of machine learning models? Not all of us will be called to build these machine learning models. In fact, many of us will be users. And so I hope to end with some practical tips and recommendations in evaluating these machine learning models for measurement bias. So we start off by beginning to think about the concepts of fairness and bias. If you look into the data science literature, fairness and bias are often terms that are used interchangeably in data science, computer science, and so forth. However, within the psychometric and psychological assessment literature, fairness is distinct from bias. And this is the perspective that I will be approaching it from the psychometric and psychological assessment literature. Hopefully, this will be helpful in informing what machine learning measurement bias might look like. So according to the principles for the validation and use of personnel selection procedures, which has been adopted as a policy statement by the American Psychological Association, or principles for short, fairness is a social concept. This is also in the standards for educational and psychological testing, standards for short. According to the principles and standards, there are 4 definitions of fairness. The first definition is in terms of equal group outcomes, meaning that the assessment has to yield the same scores for different subgroups on average. The principles and standards actually reject this definition of fairness in the context of assessment. While a lack of equal group outcomes itself may be scrutiny for possible underlying biases, it is not bias per se. For example, given systemic inequality, we would actually expect that an unbiased assessment would reveal group differences between majority and underrepresented minorities. Just like COVID tests show subgroup differences, it does not mean that a test is biased merely because there are subgroup differences, because it might be accurately reflecting an underlying condition. And as applied to machine learning-based assessments, it means that detecting subgroup differences itself does not necessarily imply that machine learning assessments are unfair. According to the principles and standards, for an assessment to be fair, it has to meet these 3 other criteria in bullet points 2, 3, and 4. So for the second point is equitable treatment, meaning that those being assessed have access to practice materials and retaking opportunities. Access to constructs, where we need to ensure that the assessment of characteristics like language does not actually restrict access to the construct being measured at hand. And the fourth point, lack of measurement and predictive bias, which I'll explain in the next few slides. Within the psychological assessment literature, we often denote psychological constructs as circles, as you can see here from the psychological construct of interest label. And the scale items from the assessment tool to assess these psychological constructs as boxes, where you can see items 1, 2, and 3. So think of functional status as a latent construct and functional status scale items as boxes, for instance. With regard to measurement bias, we are interested in how these scale items or scale item scores relate to the psychological construct of interest, as you can see in terms of measurement bias. Fundamentally, we're concerned about how these observed item scores relate to latent scores, and are they equivalent between subgroups? Now, I'll expound on this in a little bit. With regard to predictive bias, which is distinct from measurement bias, is whether the psychological construct of interest, say, for instance, personality, predicts a criterion construct differentially between subgroups. And a criterion construct might be, for instance, graduation from medical school, where personality might be differentially predictive based on different subgroups. These assessment-based biases, measurement bias and predictive bias, in standardized assessments are distinct from human judgment biases, which we call social cognitive biases. Here, which are actually human cognitive errors in judgments or attributions, or human preference for in-group and prejudice against outgroups. The focus of my talk here is on measurement bias, particularly thinking about machine learning measurement bias. So that will be the focus. So as mentioned, the concern of measurement bias is how observed item scores are related to latent scores, and if they're equivalent between subgroups. So if there's measurement bias, there will be a differential relation between the latent score and the observed score between subgroups, as you can see from the plot on the right-hand side, where subgroup 1 and subgroup 2 have different lines that relate latent score on the horizontal axis with the observed score on the vertical axis. And the observed score, really think of it as scale scores from the assessments. What you see here then, the implication is that it can empirically manifest with the same latent score. And here I've depicted that subgroups have the exact same latent score distribution. However, because the relationship between the latent score and the observed score is different, meaning that there's measurement bias on the instrument itself, it leads to different levels of subgroup scores, as you can see on the horizontal axis. So for the same latent score, we would expect actually that it doesn't matter which subgroup you're in, you should get the same predicted score. But in this case, measurement bias exists because the instrument differentially relates the latent score to the observed score based on subgroup membership. So as we understand the concept of measurement bias, we want to ask the question, how can we apply this concept of measurement bias to machine learning? And just want to present a very high level overview of supervised machine learning, so we kind of understand the different components of machine learning. First of all, so taking the example of multimodal assessments, say a video interview of physicians on their bedside manners, we extract features from the unstructured data, in this case video, it can be other things like social media and so forth, where we try to look at verbal features, paraverbal features, and nonverbal features. Right, and so verbal features could be extracted by things like IBM Watson, and we look at bigrams, unigrams, which are two-word and one-word phrases, for instance. Paraverbal behaviors could be extracted by things like OpenSmile to obtain features such as pitch, voice quality, speech rate, and nonverbal behaviors extracted with things like OpenFace to obtain facial features such as head pose, eye gaze, and facial action units. And often we want to predict the psychological construct, which we term ground truth or sometimes labeled data, where in the case of perhaps assessing bedside manner from video interviews, we have assessors use scales to rate bedside manner of physicians. And these would be quote unquote used as ground truth, that then we create an algorithm to use features from the unstructured data, video data, to predict. So in the third point, we create an algorithm that best predicts ground truth score. That is the measurement of the psychological construct. So with that as a nutshell, we can start to think about what machine learning measurement bias might look like as an analog to typical measurement bias. Here we see that features in orange are extracted from some platform. And in this case, I gave a picture of video interviews, but it can be applied to social media or any other types of platform data. And we use it to predict ground truth survey data, which you can see in terms of the other picture. And perhaps the survey data here is assessors rating physician bedside manner. Machine learning measurement bias occurs, as we define it, when the measurement procedure has differential functioning between subgroups. However, what we're concerned about here is how the machine learning model scores are related to the ground truth scores. So you see here on the horizontal axis, the observed score or the ground truth score that is provided to the machine learning model. And on the vertical axis, you see the machine learning model predicted score, the outputs from the machine learning model. As you can see, the two subgroup lines are different, resulting in individuals who have the same subgroup score on the horizontal axis, yielding different machine learning predicted scores. So simply because they are in two different groups. In other words, individuals who have the same ground truth score given by assessors on bedside manner, the machine learning model actually produces different scores, simply because of their group membership. It's important to stress here that ground truth scores are equivalent, but that machine learning model scores are not because of subgroup membership. Another way to put it is that we expect that an unbiased machine learning model would yield or would reveal the same amount of difference between subgroups on their ground truth scores. If there's no difference, the machine learning scores should yield no difference. If there's a difference, the machine learning scores should yield the same magnitude of difference. So we broadly define machine learning model as differential functioning of the trained machine learning model between subgroups. That means the model has already been trained, and here we're evaluating the trained machine learning model by examining whether it yields different scores for the same ground truth subgroup scores. And the machine learning model can empirically manifest when a trained machine learning model produces different predicted score levels for the same ground truth level because of different subgroup memberships, and or when the model yields differential predictive accuracies across subgroups. So the machine learning model, in another way of viewing it, is not generalizing beyond a specific subgroup. In other words, it functions differently between subgroups, perhaps because it was trained on only one predominant subgroup. And I'll explicate that in a little bit. So at this point, I want you to focus on also thinking through the broad sources of machine learning measurement bias, or MLMB for short. Our team has identified two possible sources, or categorized two different sources. One is data bias, defined as non-equivalence in the data inputs. And this could occur because of the ground truth, platform-based construct, behavioral expression, and or feature computing, which I will expand on later between subgroups. For instance, in the ratings of the videos, the raters perhaps were biased in the first place when rating videos. And this is entered and propagated through the models. So you can kind of think of this in terms of the different data provided to the machine learning model that were biased in the first place. Another source of bias is in terms of algorithm training bias. Algorithms are developed with non-equivalence in the relation between extracted features and ground truth. Meaning here, the algorithm was trained in such a way that it uses features differently between subgroups. So these are the two broad sources of machine learning measurement bias. To unpack this a little bit more and to focus on the conceptual underpinnings of machine learning, I want to focus on the conceptual underpinnings of machine learning to understand the sources of machine learning measurement bias and how we might start to mitigate them. From a Brunswickian lens model perspective, people often view machine learning models as a process of inferring behavioral cues. So think about this in terms of inferring somebody's personality, say from an automated interview, or a simulation of a bedside manner, or from social media. The behaviors are cues in which the machine learning model reads and then provides a score. However, the situation is much more complex than that, especially if we're interested in the different sources of bias. So using personality as an example, where we typically have is perhaps general self-report personality assessed through some kind of measure, like the BFI, for instance. However, the platform by which we obtain the data to infer self-report personality is not the same. For instance, if you're using social media to infer self-report personality, some researchers have thought of this as online personality as compared to offline personality or general self-report personality. So in thinking about the machine learning modeling, we need to be mindful of the type of platform-based construct, or just be mindful of where we're getting the specific data from in terms of the platform, whether it's social media or whether it's video interviews and so forth. From the platform, we have behavioral cues expressed. So if you take the example of social media, we have things like likes, reactions, statuses, messages, etc. However, in order for machines to actually understand what these are, we need to compute specific features, such as words, word counts, for instance, very, very simply, or counts of specific phrases. And then these are used by the machine learning model to predict ground truth personality, as you can see from the black arrow there. All these gaps actually contribute as potential sources of machine learning measurement bias. In other words, the introduction of biases can occur at each stage of this process. So the first point, data bias source is to what extent is the ground truth equivalent across different subgroups? As you can see here, where the ground truth are the boxes that are used, often scale items that we use, or health status, or some kind of observed piece where the machine learning model is trying to predict. So the outcomes that the machine learning model is trying to predict might be biased in the first place. That's the first source of bias. So the first issue related to this is measurement bias, meaning that, for instance, men use scales differently than women that result in different subgroup scores. And here, the assessment tool that we're using in the first place for ground truth has measurement bias, traditional measurement bias, and it's very important to assess whether there is measurement equivalence on the assessment tools that you're using for the ground truth itself. The next issue is social cognitive bias and annotations. So if we are using raters, for instance, to rate videos or rate individuals on a platform, such as social media platforms, we need to ensure that we're not introducing social cognitive biases in the annotations itself. So for instance, in organizational psychology, it's known that during interviews, females are often rated more severely in conscientiousness due to, for instance, stereotypes. And possible mitigation strategy is to train and standardize procedures for raters to reduce social cognitive biases, and perhaps to use more diverse raters and then to aggregate them so that no one rater introduces too much social cognitive biases and they are washed out in a sense. Another issue is in terms of sample non-equivalence in machine learning model training. So the machine learning model is trained on considerably different proportions of subgroups that may weight one subgroup more than the other. And in some ways, this affects the generalizability, right? So if you're training the machine learning model on, for instance, all white individuals, then it might not generalize to underrepresented minorities. And so it's very important as a mitigation strategy to think about, for the subgroups that we're interested in, to use the same numbers of individuals for the subgroups. Even beyond that, we need to ensure that the training sample has trait distributions that are similar. Because an example is that if you're training the machine learning model where males have a higher level of conscientiousness than females in your training sample, that is probably not representative. What's going to happen is that the machine learning model might pick up on these demographic differences between males and females in trying to use them to infer ground truth scores. And these would inadvertently potentially introduce demographic biases. So we want to also match subgroups on ground truth distributions in machine learning model training as well in that case. Data bias source 2. To what extent is the platform-based personality equivalent across different subgroups? So, for example, in the phenomenon of Black Twitter, where Black Americans often are known to perform their identities through display of cultural competence and knowledge, such as using Twitter platform as a social critique based on shared identities of Black Americans. And this research suggests that there's a greater level of display of Black identity on Twitter as compared to white identity. So in that case, it might be that Black individuals actually show lower levels of agreeableness on social media, despite having the same general levels of agreeableness as white individuals. This is because they're using the platform differently. And it's very important to consider and account for that. Possible mitigation strategy is to actually reduce the conceptual measurement gap between ground truth construct and the platform-based construct. So for instance, perhaps use online personality rather than general personality as the ground truth when you're trying to build a machine learning model algorithm. The next data source is in terms of to what extent are the behaviors expressed equivalent across subgroups. Some research has shown that for the same level of agreeableness, women nod and smile more than men on an interview. So even though in terms of the ratings of agreeableness, they're similar, women might actually have more behavioral expressions of agreeableness, such as nodding. A possible mitigation strategy is to ensure that for those constructs that you're interested in, if they're yielding different behavioral expressions, you might want to consider excluding these behavioral expressions that reveal substantial differences between subgroups. And importantly, this is assuming that you have equivalent platform-based levels in terms of the construct that you're interested in. So for instance, in this case, that you have the same levels of agreeableness in terms of raters rating both men and women in terms of the video interview, but then women display more expressions of nodding and smiling, for instance, as compared to men. And this might reveal some kind of non-equivalence in the behavioral expressions, even given the same platform-based levels. Another data bias source is in terms of feature computation. So machine learning models often require a trained machine learning model to compute features. Consider a machine learning model pipeline that actually is where speech is transcribed using a pre-trained speech recognizer, which is actually a machine learning model, and then submitted to another pre-trained machine learning model to compute a sentiment score. So the problem potentially is that if these machine learning modules that you're using are actually biased in themselves, it might actually lead to non-equivalence in feature computation, despite the same behavioral cues being provided. So it's widely known For instance, that automated speech recognition algorithms are less precise for dialects relative to the majority group speech, or what is considered codified standard speech. So this could result in a source of bias. So the issues here are in terms of non-equivalence, in terms of behavior expressions and features computed. So for instance, lower income individuals might have less features computed despite the same levels of behavior expressions due to poor internet connectivity. So this is not because of the machine learning modules that you're using itself, but really because of the platform leading people or leading the computers not to be able to detect those behavior expressions due to internet connectivity, or that feature computation modules are biased in themselves. I gave the example of automated speech recognition. So in those two cases, an important aspects of mitigation is to potentially exclude computed features that reveal substantial differences between subgroups in the first point, and then examine these feature computation methods for bias in themselves. Finally, in terms of algorithm training bias, it's really kind of using these features differently between subgroups. From a psychological assessment perspective, features are often thought of as somewhat equivalent to measurement items or scale items. So if we're differently weighting, for instance, these features, we're actually not using the same types of information to score people. So the idea of different features for different subgroups, or weighting features differently for different subgroups, would be a form of measurement bias, such as differently weighting facial expression features might lead to lower scores for younger individuals as compared to older individuals. A possible mitigation is to use a common algorithm for both subgroups, or that the trained algorithm is not actually yielding the same machine learning measurement scores, assuming the same ground truth scores. So for instance, including facial expressions or facial expression features lead to lower scores for older individuals as compared to younger individuals. And this may be revealing a priori data biases, and it's important then to look back to possibly exclude such features itself. So we want to move on quickly to some practical recommendations, and I recognize that our time is running short here. Recommendation one is to think about whether the trained machine learning model algorithm has been evaluated on subgroups of interest. So for instance, this has been famously examined. While facial recognition has high levels of accuracies in general, the data sets for evaluating accuracy contain mostly lighter skinned individuals. And aligned with this framework that we have provided, while Lamwini and Gebru propose that a balanced sample of both gender and skin type to evaluate machine learning measurement bias, or term bias in their paper, they actually found that trained machine learning models had high accuracies for lighter skinned men, but comparatively low accuracies for darker skinned women. So they actually explicitly evaluated the trained machine learning models to examine if it has machine learning measurement bias. Recommendation two, was the machine learning model trained on data that have similar characteristics across subgroups? As I mentioned, a lack of equivalence in terms of the subgroup characteristics themselves can lead potentially to machine learning measurement bias. For instance, using predominantly men samples to train Amazon's resume screener may have led to machine learning measurement bias, where men were selected at a higher rate than women. So this is very important to examine in terms of looking at the technical specifications of what the machine learning model was trained on. Third, one should consider whether the platform data inputs for training the machine learning model may be used by subgroups differently. As I mentioned, in terms of the idea of Black Twitter that some researchers have examined, Black individuals might be using the platform differently than white individuals. And think as well about some research which shows that Black Americans use African American vernacular English on Twitter, whereas white Americans do not. And it's been found that machine learning models can systematically classify content aligned with the African American English dialect as harmful at a higher rate than content aligned with white English. And this was found by Bal-Burak et al. In 2021. Fourth, as a consumer of machine learning model-based products, it's also important to ask and investigate whether the trained machine learning models differ across subgroups, meaning that the algorithms are trained in a way that is different. From a psychometric perspective, this can be evidence of machine learning measurement model, bias, because different measures are being used to assess different subgroups of individuals. For example, subgroup norming of features in machine learning models, meaning z-scoring machine learning model features separately for each subgroup, is common in computer science applications. However, this may actually be a source of bias because we're not actually using features in the same way between subgroups. I wish I could be there to answer any questions that you might have, but please email me if you have any questions or comments from this presentation itself. Thank you so much for your kind attention.